Good day, students. In this clip, we're going to be going over part 2 of the modeling and optimization problems. And in this case, we're going to be dealing with a cylindrical can situation. All right, so let's go over the steps again. I went over these in part 1, but we're still going to use the same procedure to do these problems. So step 1 is you want to model the situation using a diagram or a graph, and then you want to create your optimization and primary function, optimization of primary functions and your constraint functions. Part 2, you're going to substitute an isolated variable from your constraint or secondary function into your optimization of primary function. Part 3, you find the potential extremas by looking for critical points and endpoints. If you are dealing with a closed situation, that's when endpoints are applicable, or else you just look for your critical points. And in part 4, you're going to classify your extrema, verify if it's a max or min, either by using the first derivative or the second derivative test. But you can also evaluate the endpoints to determine if they are actually the extremas, okay? And in part 5, you just state the meaning of your results. All right, let's take a look at part 2, or number 2. It says you're to create an enclosed cylindrical tank to hold 64 cubic feet of petroleum distillate with steel sheets. What are the dimensions of the cylinder that will use the least amount of steel sheets? All right, so for part 1, we are going to create a mathematical model of the situation. Okay, so we're going to model the situation for part 1. So first thing we're going to do is we're going to sketch the graph. We're just going to draw a cylindrical tank. All right, so there goes my cylindrical tank. Now let me basically label the measures here that are relevant. So for your cylinder, it's good to know if you want to calculate the volume and the surface area, you want to know the height of your cylindrical tank. We're gonna call that H. So let's call the height H. And then the radius is going to be R. Okay, so the radius of our cylindrical tank, let's call that R. Alright, so the height is H and the radius is R. Okay, let's start off with our optimization function. Optimization or primary function. Optimization or primary function. So what are we optimizing in this problem? We're asked to determine the dimensions that will use the least amount of steel sheets. Okay, so what are the steel sheets used for? Is it going to be the enclosure, the exterior, or the volume? If we're looking at the steel sheets, we're basically looking at the surface area of the tank. Okay, so we're optimizing the surface area because that's what we're using our steel sheets to do, right? To build the exterior, the surface area. And since it is enclosed, we're going to be looking at the top, the bottom, and also the sides. All right. Okay, so now let's write down the volume of the surface area of this cylinder right here. So surface area, let's call that S. Surface area is going to be the area of the top and the bottom. The top and the bottom are two circles, so that's going to be 2 times pi r squared. Remember, the area of a circle is pi r squared. All right, how about the lateral area, the area of the. Now, if you cut this cylindrical tank by the side and laid out the lateral area, what is it going to look like? What you're going to have is you're going to have a rectangle. So if you take a look at this applet right here, this is a cylinder on the side. So earlier we said that the top and the bottom are going to be 2 pi r squared. That's these two sides. How about the area of the lateral area? Well, basically, if you cut it and lay it out, it's going to become a rectangle. Okay, let me show that to you real quick. So if I lay it out like this, what do you see happening? You have a rectangle. That's the lateral area. So 2 pi r h will be the area of the rectangle. H is basically the height, and this 2 pi r is the same as the circumference of the circle, so that's why it's 2 pi r h. Okay, see how that plays out? So this length right here is the same thing as the circumference of the circle. Okay, so the area of this rectangle is length times width. The length is 2 pi r, and the height is h. Okay. All right, so now let's go ahead and write down this is the area of the top and the bottom plus the lateral area is 2 pi r is the length times h, which is the width of the rectangle, the resulting rectangle, if you disassemble this cylinder right here. All right, so that was your optimization function. And if you notice, we have two variables here. Hopefully our constraint can help get rid of that problem for us. Okay? All right, so now let's take a look at the constraint function. So optimization, we were focusing on the surface area. And then for the constraint function, let me change the color of that. Let's make it blue. So constraint function, constraint. What is the constraint here? What are we constrained by? What is the limit? How much liquid are we supposed to hold? We're supposed to hold 64 cubic feet. So the constraint is the volume, okay? So the constrained by the volume, which has to be equal to 64 cubic feet. Okay, so there goes our constraint right there. All right, now let's write down the equation. What's the equation of the volume of a cylinder? We know what that is, right? The volume of a cylinder is given by the area of the base, which is pi r squared, times the perpendicular height, which is h. Okay? All right, this has to be equal to 64. So we have pi r squared h equals 64. Now, if we wanted to isolate a variable here for substitution in part 2, which is the easiest variable to isolate? If I wanted to isolate r, I'll have a radical and then denominator. It won't look too pretty. But how about we isolate h? Okay, so to isolate h, we just basically divide both sides by pi r squared. Pi r squared. And then we'll have, what do we have? We'll have h, change color here, sorry about this. We have h equals 64 over pi r squared. Okay? So this is a constraint function with one variable isolated. All right, now we are ready to shift to part 2. Part 2, we are going to substitute and state the substitute and domain. Substitute. And then we also need to state the domain. So substitute and domain. All right. So what are we substituting? Well, we want to express the optimization function in terms of one variable so we can differentiate with ease. So we found it easier to isolate h in the constraint function. So we're going to plug that into the optimization function so that it'll be easy for us to find the critical values by differentiation. All right. So s in terms of r, because h is going to get substituted away, will become 2 pi r squared plus 2 pi r. Now we're going to take h, develop h from the constraint or secondary function, which is 64 over pi r squared, like that, and simplify it a little bit, and that will give us our new function for the surface area. S of r is equal to 2 pi r squared plus 2 times 64 is 128 pi, and then r goes here once, so 128 pi over r. Okay? All right, now what is the domain here? What is the domain? We can clearly see that r cannot be 0 because we have an undefined value here. And r cannot be negative because it doesn't make sense for you to have a negative radius. So r has to be bigger than 0. So we know that r has to be bigger than 0. Now, how small can r get? If r gets arbitrarily close to 0, this term gets to 0, and this term dominates. It becomes really, really large. Okay? So it approaches infinity. And then if r goes to infinity, this term right here goes to 0, and this term becomes arbitrarily large. This term dominates, okay? So basically, r is greater than 0, okay? R is greater than 0. You don't have a maximum or minimum value for r. So r can be written as this, or the open interval 0 to infinity. Okay, so there goes your domain right here. So this tells us that in the case of the extrema, we're not going to be considering the endpoints since we do not have fixed values for r at the extremes. Okay? All right, so there goes the function and your domain. All right, so let's write this down. Part 3, potential extrema. Potential extrema. Those are going to be your critical points and endpoints, okay? But in this case, since the endpoints are not, we don't have endpoints here, our potential extrema, we're just going to be looking for the critical points, okay? Critical points. All right, now let's find a critical point here. How do we find the critical points? To find the critical points, what are we going to do? To find the critical points, you look for where the derivative of the function, s in this case, s prime, is equal to 0, or s prime dne does not exist, right? So those are the critical points for the function. Okay, so let's go ahead and rewrite the optimization function, since that's what we're optimizing, that's what we're going to differentiate. S of r is equal to 2 pi r squared plus 128 pi over r. All right, let's differentiate. Uh, we can rewrite this for differentiation, so this will be 2 pi r squared plus 128 pi raised to r to the negative 1. Okay, so we can use the power rule here as opposed to the quotient rule. All right, so s prime, first derivative, s prime of r is equal to, that's going to be 4 pi r. 4 pi r, applying the power rule here, you have negative 128 pi, and then you decrease this degree by 1 by the power rule, negative 2. So that equals 4 pi r minus 128 pi over r squared. All right, so that's your derivative. Now that we have the derivative, we're going to find the critical points, okay? So to make it easier to find the critical points, let me assemble this into 1, so I can put this over 1 right here. And then let's find the LCD. To make the denominators common, I'll times this by r squared, top and bottom, r squared. So our derivative, s prime of r, can be written as a combined numerator, which is 4 pi r cubed minus 128 pi, that divided by the denominator, which is r squared. R squared. Okay, so you're going to see why I did this in a minute. Now let's look for the critical points. So we're going to split this in two. First of all, we'll look for where s prime um, of r is equal to 0. And then afterwards, we'll look for where s prime of r does not exist. Okay, so for that, where it's equal to 0, we're going to take the numerator, right? Because if we write down the whole thing, 4 pi r cubed minus 128 pi over r squared equals 0. If we cross multiply, we're going to end up with 4 pi r cubed minus 128 pi equals 0. Okay, so when you write it as a combined fraction like this, as a rational fraction expression, you can extract the numerator anytime you're looking for where the derivative is equal to 0, or just do the steps I just did right here. Okay, so we add 128 to both sides. 4 pi r cubed equals 128 pi. And then if we divide and take the cube root, we're going to end up with r equals the cube root of 128 pi over 4 pi.